Okay, I will present a little bit about satellite rainfall estimation. This the title of my presentation is SSMIS satellite rainfall retrievals during CHUVA GLM experiment. This is valid Paraíba. Authors like Nicolas Romulo, who helped me during the last minute with some graphics, Luis and Wagner. So, okay, this is just like the outline of the presentation. I will make a short description of the algorithm for rain rate retrieval from passive microwave radiometers on board of low orbiting satellite, like is the SSMI sensor on board EMSP. Then I will present a case study over Valle de Paraíba during February 11, 2012. The comparison of the different rate retrieval for heavy rain during CHUVA GLM period, because during this very preliminary result, we are using two different algorithms. Both are based on Bayesian retrievals. One is the GPROF, and the other one is the brain algorithm. So we can move forward, and well, the first important things about both algorithms, both use Bayesian approaches, but both of them are prepared for SSMI and not for SSMIS. There's no version for SSMIS. So I will show you some, what we did to adapt those algorithms for using SSMIS. And this is very important because we have three satellites flying right now, F16, 17, and 18. So if we want to get some kind of generating for SSMI and SSMIS, and it's used in the Global Precipitation Climatology Project as also in the TMPA project from NASA. So this I told you before, this is based on a Bayesian approach to match the observed brightness temperature to hydrometeoric profiles derived from cloud resolving models, and radiative transfer model based on one-dimensional internal approximation is used to compute the brightness temperature from CRM hydrometeoric profile at the observed frequencies. So in this case, we are using the version for GPROF 2004. So it's model-based, it's not observational-based like the brain. So this is just like a little flow chart, how we deal with the data. First of all, we need to decide which type of surface we are dealing with, and we perform the retrieval. On the other side, we have also the brain, that we will have a presentation, I believe the next one is about this retrieval model. It's the precision retrieval algorithm using the neural network, and this is very similar to what I said before. First of all, we need to decide which type of surface we are, if we are over land, over coast, or over ocean. In case of if we are over land, we use the high frequency channels, 85, H and B, and 37. And of course, if we are over ocean, we use all channels. So this is just a slide where I try to show the difference between both algorithms. Both are very close because are developed in the same principle, the Bayesian approach. And these both are database-based because we have a database with the profile, so we try to match the observed vector of brightness temperature with a predefined database, and retrieve profile at surface and rain at 12 kilometer resolution. This was done during the visit of Nicolas during last year. We we create some kind of version of brain for high resolution in terms of microwave, because we have low frequency channels and high frequency channels. The high frequency channels we have a 12 kilometer resolution, but for low frequency channels we have around 25. So we try to come up with a version of brain for this high frequency, special resolution for brain. The database, of course, different principles. GPROF, as I told you before, it's a pure model. It's a mix of observation in case of brain. So the histogram matching approach, this because both algorithms were developed for SSMI, and we have right now SSMI-S. We don't have any SSMI sensor flying right now, just only F15, and it's not a very good quality. So as we can see here, if we plot the antenna temperature in this case, we can see that over ocean, over land, the histogram differs because we have a different frequency. For high frequency, we have 85 for SSMI and 91 for SSMI-S. So because the frequency is higher, we expect more scattering in case of retrieval rainfall over land. So we need to take into account these kind of things. So the basic idea is to match those histograms using this histogram matching approach. Just a slide how to do that. And we come up with lookup tables for all the channels. So stratified by surface type, land and ocean. And well, we create using a common period where this lookup table is in a common period with both SSMI and SSMI-S who are flying together and very close in time. So we came up with, right now, very close histograms. So these lookup tables look like this. This is for the more related rainfall channels. This is 19B, 22B, and 85B. So for different temperatures, we have different corrections. So we deal with this table to correct the channel for SSMI-S. So we come up with SSMI. We start with SSMI-S vector. We apply this histogram matching approach, and we create some kind of synthetic SSMI channels that we can put into the models to come up with the precipitation. So this is the case study. This is for brain and for GPROF. We are seeing almost the same pattern, but different values. So we are analyzing this kind of thing because we believe that something is not working fine with some of the steps we did during that process to reading the data and apply the lookup tables and so on. So this is the scatter plot. We have very good correlation, but it's off from the 1-1 line. So we need to analyze these cases. We finished with this analysis during last week. So we need to figure out what's happening with this, because in case of GPROF, we have pretty nice histograms, but in case of rain over land, this histogram doesn't look like a rainfall histogram. So we need to look at this, and this is also another information we are looking at, because of course the basic idea is to put everything together, or most of the information we have to put everything together. This is a GPROF and this is MSPPS. This is the original one, and we can see that some difference in the pattern, but also some differences in the rainfall amount. For example, over the ocean, we have a big overestimation with AMSU, because this is based just only in scattering, and this is more related in emission. So and the pattern it's a little different because this image is 1 hour and a half before this one. So when we make this kind of comparison during heavy convection period, perhaps the pattern could change with time. This is brain again, and this is the closer TMI passage. So as you can see, the structure is almost the same thing. Well, we need to figure out what happened with the values. So and this, okay, thank you. This is for heavy rain rate case. We took those cases with brain with more than 1 millimeter per 1 millimeter of rain rate, average rain rate over the whole area, and see what happened. So we have the same problem we had in the case study. In this case, we have 35 cases. We have overestimation using brain, but it doesn't seem that it's related with the maximum value that we have in the image, in the SWOT. So we need, as I told you before, we need to go further, go deeper to analyze this data and see if we are doing in the right way. So this is the bias score, and this is POD and FR, false alarm ratio. It's not validation stuff. It's just a comparison. I put that like observed as brain and predict as QPROF, but it's not observed and predicted. It's just comparison of these two results, where we can see that for very high rain rate, the bias score is very large, and we have large values of POD, very low, high values also for high rain rates. So this is what I have to present right now. We need to go further in the research and see what happened with the brain version, to come up with more results in the future.
Time for question.
Done. Yes, the point, I have an idea for this case study. I have the radar, but it's very small compared with these two. And so this is because I didn't put in my presentation, because we have, very few points with rainfall over the radar, because the radar is almost in the middle of this figure, around here, somewhere around here, and the radius is not so large. So very few points for the radar in this case. So we need to find out the golden cases for the CHUVA, Valero, Paraíba, and see what happened in those cases. If we have a passage of SSM of DMSP applies.
Other question? I have one question.
Okay.
A more general,
yes.
very general. There are people in the satellite community that prefer to compare rainfall estimations from satellites with rain gauges, skipping the potential advantages of radar, because with radar you have theoretically a better view of aerial precipitation, but many people prefer to stay with rain gauges. What is your opinion?
Well, the point is, when you compare with gauges, you need to get some kind of accumulation. And when you are doing accumulation, you are putting many things, many different things, because you don't have just only one satellite over all the period. So you need to come up with some kind of merging technique. So you are putting everything together, and sometimes those things you are putting
In the right
pod.
way,
They are not the same thing. So you average everything and you compare with the gauge. And of course, the results are better if you compare on instantaneous basis, like here. So this is one of the goals of my research. Try to investigate what happened on instantaneous basis. This is because I would like to use the radar from CHUVA and other radars, but it's good to know that the satellite community right now is moving towards radar retrievals and using the radar retrieval for validation stuff. So I believe that in the near future we will see many papers and many research work using radar for validation instead of gauges.
Okay, thank you. I'm happy for this because I work with radar, so I have